All right, so we'll be discussing today on the vPC, how vPC works. It's one of the most important topics on the data center CCIE. The initial section is discusses all about how vPC is set up and what are the benefits over the older STP technology, why they came to this idea and all that. What are the various features. We'll be discussing all those in detail in this session. Right, so today's agenda is we'll be talking about vPC concepts, the differences between the vPC and the STP technology. We'll be discussing about certain design constraints. We'll be discussing about the consistency check, which causes a lot of problems if it's not properly configured, and all the issues that we face. We'll also see how the forwarding works in regular or normal scenario in a certain data center design, and also in the failure scenario. So that is all that we are going to cover in today's session. All right, so vPC concepts. Right, so before we begin, just to give you an overview on what all technologies or what all is supported from the STP perspective on Nexus. So Nexus 7000 or any other Nexus device supports rapid PVST. This is the default mode, right? Then we have MST support. Also, we have PVST. It's not supported, but provides interoperability. All right. Nexus OS always uses the extended system ID in the spanning tree design scenarios. The biggest challenge with the spanning tree protocol is, say for there is a spanning tree topology, right? And suppose this is the root bridge, switch 2 and switch 3. I'll make the switch 1. All right. So in any regular spanning tree topology, the biggest challenge that we face is the underutilization of links, and in certain design scenarios, the introduction of spanning tree loops, right? So in any spanning tree design, what happens is, in order to avoid though spanning tree supports loop avoidance mechanism, that's the reason it puts one of the links in the design into blocked port, so that the actively traffic is forwarded across to the other links, and it doesn't create a loop over here. So this link getting blocked, there are certain algorithms or steps which decides which link will be blocked. I'm not going to discuss that over here in this session, but I'm just giving you an overview of how STP is working.
The blockage is one way only?
Yes.
Okay.
So no, the whole link is blocked. So neither traffic will go this way nor this way.
Oh, okay.
It's blocked for both of them. Okay. So this is how the older STP used to work. It's still there. It still works with vPC designs, but vPC provides much better functionality to STP to overcome this blocked and unutilized links design, and thus provides much better link utilization and resource utilization, right? All right. So vPC is nothing but a port channel mechanism. With vPC, what you do is you create a port channel between virtual port channels between two peers. What it looks like to the end host or the access layer switch is it is actually directly connected to a single switch, but actually these are two switches looking virtually a single switch. And this also provides a mechanism of having, like VSS in 6500, you can have the port channels going to two different chassis or two different VDCs, in fact, and creating a port channel, right? Thus providing much better utilization of the links and forwarding mechanism, right? So since both the links are in forwarding state, like in older STP, this link was in block state. Over here, the traffic gets forwarded across both the links. So
you are not pointing the thing. Can you repeat that there?
So if you see here, in the non-vPC designs, one of the links used to get blocked, right? Like I explained for the STP. But in vPC design, all the links are in forwarding state. This one as this one. So traffic can be forwarded from here as well and from here as well, based on the design or the traffic source and destination traffic that you have, right? So I'll be forwarding the forwarding mechanism under vPC later in this session, but right now I'm just giving you an overview of how vPC looks like, right? So vPC again maintains its own control plane protocol, maintains own independent control plane. Basically, we need to remember it's completely layer 2 technology, not a layer 3, right? So whatever the vPC that you're creating, it's just layer 2, more like a layer 2 port channel, right? Feel free to stop me wherever you face any issues or you have any questions.
Can you go back to the previous one? I didn't get this.
Yes, go ahead.
What does the last product means? Independent control plane?
So vPC runs the control plane between its peers for the Keepalive and maintain its high availability feature with its own control plane mechanism. We have all those topics covered later in the presentation.
Okay.
All right. All right. So what are again, what it provides is, as I mentioned, there are no blocked ports, right? It's a layer 2 port channel only. Again, it provides faster convergence. Again, with this link failure scenario or the device failure scenario, you get better access. And obviously, it's a port channel between the two peers. Now, the two devices which form the port channel between them, we call that link as a peer link. The peering over that port channel, the devices that peer with each other, is called the vPC peer, right? The vPC can be formed on Nexus 7000 or the Nexus 5000, right? In order to, on a Nexus OS software, by default, a lot of the features are in disabled mode, right? So if you do a show feature, you'll be able to see which all features are enabled and which are not. And based on that, you can enable the respective feature. Like you want to enable NTP, right? So you need to do feature NTP, and that will enable the NTP-related configuration and the feature itself. So in order to enable VPC, you need to do feature VPC, and after that, you'll be able to see the VPC-related configurations enabled. Otherwise, neither the process runs or nor the CLI is available to you. Apart from that, you also need to remember that you need certain licenses for running certain features. If you don't have the license and you just need it for testing purposes, you can use the grace period license. You need to enable that grace period license from the CLI on the Nexus switch. Okay, the features, the VPC feature was available on Nexus 7000 starting 4.1 for Nexus OS and 4.13 N1 on Nexus 5K, right?
Okay. So the main advantage is that you are utilizing all the available spots without any blockage.
Yes, and that's one other reason that you need a smaller topology design. Like in order to make better utilization of the links and to provide services to all the end host or end access layer switches, you needed to have more distribution layer switches because most of the links used to get in block state, right? But with this, you need a smaller design because it provides forwarding across all its ports, and it's highly converged. Okay. The differences between STP and vPC. So STP blocks redundant uplinks, VLAN-based load balancing, loop resolution relies on STP. Again, if there's a protocol failure or there are certain design flaws, you are into a bigger mess because, again, the loop in a spanning tree topology creates a lot of issues in the network convergence, and also creates a huge impact in the production environment. With the vPC-based design, you don't need to worry about the uplinks or the blocked ports because there are no blocked ports anymore. Lower oversubscription because all the links are properly utilized, so not just one single link will get overutilized. The traffic can be distributed across multiple links. It's a ether channel load balancing mechanism, so there's a hash calculated for each flow, and based on the hash, the traffic is forwarded across. And the best part is it's a loop-free topology. So we'll understand much better on the loop-free part when we see the forwarding, how the forwarding works on vPC.
In the picture below, in the below picture, you are establishing the vPC. Mm-hmm. This is basically all that 4 links constitute to a logical link.
These are physical links.
No, these 4 physical links constitute to a logical link. It's like a multi-link kind of thing.
Right. So this topology will actually be like, so all these 4 switches, they will feel like they are connected to a single.
Yeah, that's it. Yeah, yeah, okay.
Distribution layer switch.
Yeah, distribution layer, which is one will be the replica of the other kind of thing.
Well, there's no replica because the VPC is again local to that particular VLAN.
Okay.
You define the VLANs whichever the VPC will be allowing.
Okay. Okay. You might see more details.
What do you mean by replica?
The replica meaning the top one, right? 2, 4 at the bottom top layer, right? So one is physically that one what you are drawing the right side, all the 3 is effectively it is physically the one switch on the left.
So basically at the bottom to the bottom, the primary route and secondary route appear to be like one switch.
Yes.
From appearance perspective,
the distribution layer switch, it's totally seen as one single switch, because generally when you create a port channel, it's across just one chassis to chassis, right? But with vPC or with older VSS 6500 VSS based design, you can create port channel across multiple chassis, and those nodes used to be seen like a single chassis.
Okay, yeah. This is something like the VSI in the past. The ATM world, where something called virtual switch interface. So anyway, yeah, go ahead. Yeah.
All right. So the different terminologies that will be used in vPC are the vPC peers. So suppose these are the 2 Nexus switches, Nexus N7K1 and 2. Right? These are called the vPC peers. If there are any further I can show in this particular design, again, these 2 are also called the vPC peers, right? So these are the vPC peers. The port channel between the vPC peers is called the vPC peer link. For the Keepalives or the heartbeat messages, there's a separate link configured, which is called the vPC peer Keepalive link. Okay.
So, 1 second. Can you go back to the previous one? So the picture that you showed earlier, can you just go back to the previous one?
Sure.
Yeah. So this one, the bigger switches out there at the top, what you are talking about, right? Those are actually the active standby kind of thing. Is that what it is?
On this topology or this one?
on the bottom topology.
Yes, so the one will be primary and one will be secondary.
Yeah, okay. Yeah, that's what actually my original question was. Okay, makes sense. Okay,
yeah.
Go to the next. Yeah, okay.
More like HSRP, right? One will be active and one will be standby.
Okay.
All right. So the links configured, the members which are configured towards the access layer are called the VPC member ports. Those ports which are not participating in the VPC are called the orphan ports because they don't participate or they are not part of the VPC design. CFS is the Cisco Fabric Services Protocol, which is one of the most important protocols in VPC and other protocol features as well on Cisco Nexus boxes. What CFS does is maintaining the state, replication of the configuration, state synchronization, all that part is automatically taken care by CFS. Now, CFS can work over Ethernet or IP as well. We'll see that again as we progress further in this presentation. All right. Now, what are the different steps to form a VPC domain? First step is to create the domain ID. Now, note that for like this is N7 Nexus 7K and this is Nexus 5K. They can form their own VPC domains. So this is one domain as highlighted, and this is another domain. The next step after creating the VPC domain is to establish the peer Keepalive link connectivity. Now, the peer Keepalive link is this one. Not the port channel, the different link that is separately used to configure the peer Keepalive for exchanging the heartbeat messages between the VPC peers. All right.
So this is like a control protocol which is running off of STP?
No. So it is not working on STP.
No.
It is just like simple from source to destination. You are sending Keepalive messages. Okay, are you alive or not? Just to check my peer is alive or not.
So this is for the HSRP, the standby active relationship only.
This is not again HSRP.
No, what I meant is the top one what you are talking about, right? Top one, the ones which is connected. So the peer links which you are talking about, aren't these peer links between peer links are active and standby?
Yes, it is between the active and the standby, or the primary and the secondary.
Primary and the secondary, yeah, okay. So the Keepalive is between them only. That means basically it's a higher layer control mechanism.
Yes. Okay. Right. I mean, like you can take a Nexus 7000 chassis, or say for CRS or a GSR chassis, for that matter. There's a RP card, and there is line card. Now, the Keepalive mechanism, IPC runs between the RP and the line card to check whether the line cards are active or not. Right? That's how they understand the nodes, the line cards are present or not, or if there's any problem with them or not. So similar way to keep track of how, if my secondary VPC peer is there or present or not, the Keepalive link keeps track, it keeps track over the Keepalive link.
So in implementation, what you're looking at is that in 7K, what you're looking at is the two supervisors, that is the ones which are acting as the Keepalive host, one to the other?
So there are different ways to configure the Keepalive link. It can be done on the management link. It can be done on the routed link. It can be done on SVI based. Or it depends what you're doing. What you're from where you're trying to configure the VPC Keepalive link.
Okay, I don't want to jump ahead, but maybe you can show the examples at that time. So
yeah.
Okay. I haven't seen. So.
No problem.
Okay.
All right. So second step is to establish the peer Keepalive connectivity. The third link is we form the port channel that is called the peer link. So that is between the Nexus 7K and the 7K. So understand one thing. It's not like you can create a VPC peer between an N7K and an N5K. That is not possible, right? It has to be between an N7K and an N7K, N5K and an N5K. Second thing, more important thing is the VPC domains that you configure has to be unique in the design. So if you configure a VPC domain of 10 over here, you should not configure 10 over here. I'll explain that why. I mean, that will get more clear to you why is it that way, because you might run into certain issues or the device might get confused as to which VPC link it has to forward the traffic to, right? So it is recommended to have different VPC domains for all the VPC domain setup in the data center environment. Okay. And the last step is to reuse port channels and create VPCs. So these port channels are the VPCs, right? These are the part of the VPCs, and you can configure up to maximum 16 ports per VPC.
But you mentioned earlier that you cannot have between N7K and N5K, you cannot have VPCs.
No,
so
the VPC peer is between N7K and N7K.
Oh, peering.
The VPC peer.
Peering.
Yes,
peering,
the port channel can be between two different kind of devices.
Okay, the peering is one. Okay, got it.
Yes.
Okay. I think I got it. Okay.
I have one question. On the N7K, does the supervisory hardware need to match between the two?
Yes.
Is it also a requirement that the memory on the supervisors and everything has to be identical?
Well, I don't think that should matter much, but in a data center design, whenever you are designing a data center, it is recommended whenever you are creating primary, secondary kind of nodes, they are identical in the hardware configuration.
So there might be something like an.
The reason is think of it from a perspective of the real design or the implementation. Now, what happens is you have, say, 100 megs of memory here. Let me clear this up. Okay, you have 100 megs of memory here, and you have 200 megs of memory here. And what happens is this 200 megs stores the MAC addresses of all the hosts that is being learned over this VPC peer, right? Using the CFS, it also replicates the MAC address to the peer device, the VPC peer. Now, what happens? Will this device be able to store as number of MAC addresses as this is able to store?
Depends.
Right? Make sense?
Makes sense.
Okay. Right. And the very last step of this all is make sure the configuration are consistent between both the devices. If there is inconsistencies or there is mismatch configuration, you may run into type 1 or type 2 type of consistency issues, which again, it's coming up further in the later slides.
Are these kind of boxes supports the non-stop, what do you call, non-stop upgrade or something like that? Aren't they giving? So if they were to say, if you have a 100 meg card on one side and then you are actually upgrading to a later version of it, so then you might actually have this working scenario, right?
Sorry, I didn't get your question.
So how do you do the upgrades? I mean, do they support these boxes support the kind of non-stop upgrades kind of thing?
ISSU, you're talking about in-service
I don't know whether it's
software.
called in-service actually. I mean, in fact, I don't think, I mean, at that level it's called.
ISSU upgrades are supported, but talking about the line cards or the hardware or the supervisory hardware, generally it has to upgrade on both the sides.
So that means it is basically taken through a full system reload kind of thing.
Yes. I mean, you have redundancy supervisors, so on Nexus 7000, so you can do one at a time. That is possible.
No, but your VPC peering will stop then, right?
No, why will it stop? Because hang on to that thought, okay? Hang on to that thought. I will discuss that scenario in one of the slides. Okay.
Now, probably show some real live example. Maybe that might make it more sense. Okay, that's fine.
Yeah, I'll explain that. Yeah. It's coming up. Just hold on to that thought. Okay. So VPC domains. As I mentioned, the VPC domain IDs has to be unique in all the VPC domains. This is 10, this is 20. It has to be unique. Do not configure the same domain IDs. It automatically configures the system MAC address for the VPC. It uses a certain or a very simple algorithm to decide upon what is the MAC address that you need to, what will be the system MAC address. You can also manually configure the system MAC address, but by default, the last value is taken from the VPC domain, and that is used as to define the VPC system MAC address. Okay, so by default, you don't need to worry if you're configuring the right domain IDs and properly segregating the different VPC domains. You don't need to worry about configuring the system MACs. But otherwise, if you are configuring manually, then do remember to configure the same VPC system MAC address on both the VPC peer devices.
So the last one is the system, the MAC ID for that last?
Yes, yes.
That's 14 that you highlighted?
Yeah, so this is the domain ID.
Domain, okay.
Right. One other thing I forgot to mention, the port channels here are formed over LACP. So just do not forget to leverage upon the LACP protocol for forming the port channels.
So that means anyway they have their own layer 2 Keepalive mechanism by themselves between the port channel there. That's what they're using it?
I didn't get your question.
Is that for the Keepalive for the?
No. That's for configuring the port channels. Yeah, that's for just configuring the port channels.
No, but LACP itself gives you that flexibility of Keepalive, right?
No. So the Keepalive is different from the VPC peer Keepalive.
The link aggregation protocol, right?
Yes.
So Keepalive mechanism is, you have to understand that there's a split in your what you call it, data plane and the control plane, right?
Yeah.
Assume the Keepalive to be a control plane. You just want to keep it separate so that you don't go over the same links.
No, the Keepalive is between the same chassis host, right? Same chassis control supervisors, right? The peer Keepalive.
No.
You're talking about the other one.
The Keepalive. Go ahead.
It's Keepalive is between the two two chassis in the same system. Keepalive is between two chassis on the same system.
In absolute terms, you have an N7K, so that two supervisors there. So the peer Keepalive is that between the active and standby, or the what do you call it?
No. Hang on. You're confusing between the Nexus 7K supervisors and the VPC peers. These are two separate entities. They are two separate nodes. They can be on the same chassis, segregated by VDC, or they can be on two separate chassis.
Okay. There you go.
If you are using a VDC, it will be using the same shared resources of the supervisor. Otherwise, They are two separate chassis. Just treat it like two separate chassis. That's it. Do not confuse between the supervisors or the nodes or the VPC peers. Those are two different things.
Okay.
All right. So in this topology, right, on the access layer, what you can do is, I mean, if you do a show LACP neighbor, you will be able to see both the neighbors of going to two different switches. But if you see their ID, it's the same that is seen in the VPC system MAC address, right? So this is how you understand. Okay, these are part of the VPC port channels.
Domain.
Yes.
The 14 is the domain ID, right?
Yes. So again, this is in hexadecimal. Okay. All right. So this is how you define statically the VPC system MAC address. Do understand we need to configure this value on both the VPC peers, the exact value. It cannot be different. Okay. By default, the way it's configured is automatically assigned is using this formula, you can say. The last 2 bytes is used for the domain ID. Okay. Okay, VPC roles. So VPC role is generally defined as primary and secondary. One can be primary and one can be secondary. This applies, again, this one on N5K as well. Also note that the role is defined or automatically selected based on this logic. That is, the lower priority wins if it's configured, and if it's not, I mean, if both the priorities are equal, then the lower system MAC wins and takes the role. Okay, so the role is not preemptive. It's like, I mean, if the primary has gone down and the secondary has taken over, and when the primary comes back up, it's going to take over again. That is not going to happen. It is non-preemptive. Right. So whichever is acting, so there's a difference between the acting or the operational primary and the operational secondary, whereas as compared to the configured primary and the configured secondary. Okay.
So this primary, does it have an inherent or a hidden meaning of a root?
Root of what?
Root, whatever your bridge root or whatever root bridge or.
So generally, as per the designs, spanning tree root is defined on one of the 27Ks in this kind of topology.
Oh, okay. I see.
Right. So it can but again it's
okay.
Yes.
Okay. Got it.
So whichever is the primary VPC peer, that takes care or that takes the lead to process the BPDUs. The other will not advertise any BPDUs. Okay, even if the host is or the access layer switch is directly connected to it, the processing of the BPDU is taken care by the primary, not the secondary. All right. So peer Keepalive link. Now, in Nexus 5K, what you can do is generally the peer Keepalive links are configured on the management 0 interface. That is for the out-of-band management network, and all the Keepalive messages are flown over that. Generally, it is recommended not to directly connect both these links better to connect it over using a layer 2 or a layer 3 switch, and over there you can have the packets flowing. The other way to configure the Keepalive link is you can have a 1 gig link acting as the peer link or peer Keepalive link, or you can also use SVIs to do the same, right? But most of the designs in the production environments which I've seen is most of the customers or the companies deploy it on the management interface, right? The peer Keepalive link is configured, or the peer Keepalive is configured using the configuration under the vPC domain, peer Keepalive destination source. Like you define the GI tunnel for the source and the destination, the same way you specify the destination, you specify the source, and with this VRF management, it says that, okay, it's going to use the VRF the management into network for the Keepalive messages for this particular vPC domain. Okay.
Mm-hmm.
On Nexus 7K, now there are two parts. This is where you asked a question on the primary and the secondary, right? The supervisors. Now, generally, when you are configuring peer Keepalive link, even on the management interfaces, we need to have two separate links for the Keepalive links, for the Keepalive mechanism, both from the primary as well as from the secondary supervisor on both the switches. And do remember, do not configure it or do not connect them directly. Like there's an N7K supervisor module 1 and supervisor module 2, and there's N7K2 supervisor module 1 and supervisor module 2. Do not have this connectivity. Right? Always use a layer 2 switch or a layer 3 switch to have the connectivity, and one will be acting as the primary and the other will be acting as the standby management interface. Now, why this design is recommended? Now, think of it as a scenario. Say for this is primary supervisor, this is secondary supervisor, right? N7K1, N7K2. This is primary supervisor, this is secondary supervisor, right? Now suppose they are directly connected.
Now what compromise, right?
What is that?
Your peer Keepalive mechanism is compromised there, right?
Yes. So what happens if suppose for some reason the peer Keepalive link or the primary supervisor module crashes and does a switchover, right? So this link will become active, but on this node, this primary supervisor card is still up and acting primary. So the management interface on this node will be up, whereas the management interface on the standby supervisor card on N7K1 will be up. So both of them will be thinking that, okay, the peer is down, so I'll become the primary, both act as a primary, and create a chaos. Right? We don't want that. So the best design is to use a switch in the middle, so that whichever supervisor makes a switchover, it doesn't make any difference, because again the other side is connected over to the same port, which is still active.
So I think in fact we have a similar problem in here in the standard active standby roles for the processes, right? So what they do is that they actually give the same IP address for both of them, right? Though they have the different MACs, and then give a priority selection internally. That's how we do it on the management Ethernet for the RPs and the bigger box.
Yes.
So the problem is somewhat similar there, right?
Yeah.
Okay.
All right, so there are two other mechanisms. You can use the 1 gig ports, or you can also use an upstream layer 3 network for peer Keepalive links. Generally, even if you use the management ports, it's a better option in the data center design. Right.
So all these supervisors comes with a typical management aux, management Ethernet 1 or 2, and then
yes,
that's what it comes with all?
Yes, it comes with the management 0 interface.
Management, okay. Just only one?
Yes. All right. So vPC peer link. Now this is the port channel that we configure between both the vPC peer devices. What this does is they carry the STP BPDUs, IGMP updates, and all the information. The CFS also runs over, the CFS-based messages also runs over this vPC peer link. So in all, the vPC peer, peer link carries both the data and the control traffic for the peer switches. All right. Generally, can carry the non-vPC VLAN traffic, but it is not recommended to do that. All right. So the port channel that you configure between the vPC peers, you can make them vPC peer links using this configuration command. Okay. All right. Any questions so far? Okay. All right. So to check the vPC peer link status, show vPC brief. You'll be able to see the adjacencies formed and the peer is alive or not. You will also be able to see the role of the vPC. And the other important thing that you get to see is the configuration, the consistency check status. If there is any issue over here, you might see the status as different values. It may be in suspended state based on what kind of consistency error is there. Okay. Now, we can also see what are the VLANs ported. Show system internal VPCM info peer link. This gives us what are the number of VLANs that are being used or configured for the VPC, all that basic values. All right. Cisco Fabric Services. Now, Cisco Fabric Services plays an important role in VPC. The CFS takes care of exchanging all the control plane information, the MAC address table, or synchronizing the MAC, or validating the configuration and notifying if there's a consistency check, a success or not, also maintaining the status of the VPC, IGMP snooping, all that information or all that work is taken care by the CFS, right? So if your CFS is not working properly or if it's not enabled, your VPC will not work. So first important thing is you need to ensure that CFS is working and enabled. For CFS to work properly in a VPC design, you need to ensure that the distribution over Ethernet is enabled. Right, so you can check that from the show CFS status command, and you'll be able to see if it's enabled or not. If CFS is enabled over IP, this should also be seen in enabled state. Right.
So
all right. Any questions still left?
Where it's not working?
No. So we needed distribution over Ethernet. CFS OE, right?
So the distribution over IP has to be.
It's a layer 2 port channel, right? So why do you need IP right here?
Okay, I see. Okay, got it.
All right. Any questions so far?
Need to do something just to see how
Okay.
the vPC configures. Okay.
Okay. So consistency checks. The consistency checks is again one of highly complex things that can cause a lot of issues in the vPC environment. There are two types of consistency checks. What really consistency checks means, your configuration is correct on both the nodes or not. If it is not, then the failure may occur or the forwarding may be impacting because of the mismatch in the configuration, right? CFS provides for protocol state synchronization between both the peers. So MAC address table, IGMP state, as I mentioned before, same stuff. So if both the configurations are not matching and the synchronization will see that what is configured is not matching from what the other side is configured with after the CFS has tried to synchronize the information, then it will give you consistency check failures. Okay, so there are two types of consistency check failure messages. One is type 1 and one is type 2. Now, with type 1, it is the highly impactable. What it does is, if there's a mismatch in the configuration and it leads to type 1 consistency check failure, it will suspend the vPC peer, vPC links, and the forwarding of the packets will not happen. With type 2 consistency check failure, your vPC will still work. It's a scenario wherein suppose you have missed a particular VLAN, right? You might have not added it. So it might partially function and might impact the other one which is not configured. We'll see both the consistency check types in the coming slides. All right. So vPC type, the consistency type 1 check, it says for, if you see both the configurations here, you'll notice that one side is configured for root guard, whereas the other side is not, right? So when you do a show vPC brief, it says that the interface port guard is enabled, or the root guard or the loop guard is enabled, and the other side is not configured for the same thing, and it may lead to the suspension of the vPC. Note that because of this consistency checks, it is easy to understand what kind of failure is occurring. So if you do a show vPC brief, you will be able to clearly see what is the cause of the type 1 failure, right? And it also gives you the information on what is the vPC type, what is the type of consistency check failure that has occurred.
What is that type 1 meaning?
Type 1 meaning that there is a certain configuration which changes the behavior of one of the vPC peers, which may not match with the other one and cause the vPC go into suspension state. So the vPC will not function properly. It will not do the proper forwarding.
If you see a type 1 error, then that means it's just a question of configuration matching.
So mostly the consistency checks are mostly because of the configurations.
Oh, okay.
Right? But the type 1 and type 2 defines the severity level of the impact of those configuration issues.
Mm-hmm.
So type 1 is more severe than the type 2. Okay? Any other questions? All right. So type 2 consistency checks, this generally happens if you have skipped one of the VLANs, right? if you see both the configurations, the allowed VLAN is from 100 to 105, whereas the other side is just 100 to 104. So logically, both when the CFS occurs, the vPC will only be able to carry the traffic for 100 to 104, whereas 105 will not be going through across the vPC peer links or the vPC over the vPC port channel, right? So for the type 2 consistency errors, you will get an error message in the logs, though if you do a show vPC brief, you won't be able to see any consistency check failures. It is only in the in the error logs or the syslogs that you will be able to see the consistency check failure messages for type 2 consistency. Okay. Global consistency checks. This is a scenario wherein suppose you have a global configuration for the STP or the base STP protocol that you're running, and those are not matching, right? That may again lead to the global consistency checks. That is different from the type 1 and type 2. So generally it is recommended to have all the configurations properly synchronized or properly notice that both sides of the Nexus peers are properly and equally configured or configured the same way. All right. Any questions so far?
So the part of the global configuration, meaning what are the other things that you have shown? What are the other ones global, meaning what are the other configurations?
So, I mean, as I mentioned, you are able to run 2 different protocols in STP, right? The PVST plus, Rapid PVST plus, and MST, right? So MST region you are defining, like in this example, if you see the MST region VLANs, you are defined as 1 to 5 and VLAN 12. The other side you have defined 1 to 5 and 10. Now what will happen is as the configuration gets synchronized, this will cause an error in the forwarding. In fact, a loop probably, because it will try to go to the other side or the primary side and again fail. So it will actually go into the disable. Finally, it will cause the disabling of the interfaces on the vPC peers.
But it will also cause a consistency failure, right?
So that will be the global consistency failure.
Okay.
Not the type 1 or type 2. The type 1, type 2 are more specific to the vPC domain configurations.
Okay, got it.
Okay. All right. So if you see this slide, you'll be able to notice that there are differences in the VLANs, right? So again, this global keyword, it tells that you are looking at the global parameters for the vPC, and these are the QS related section. This is the spanning tree related parameters, and these are the VLANs that are allowed. Now, if there is any mismatch in the configuration, so if you see from here, VLAN 1 to 504 are allowed, and 9 is missing over here. So it will cause a global consistency failure. Okay. Okay, this is just an example on showing the type 1 or the type 2, as I mentioned before, the type 1 consistency can automatically be seen in the show vPC brief output. It will show you that the consistency check has failed, and it will give you the reason. For the type 2 consistency, you can use the show vPC consistency parameters and use the interface port channel or the port channel that you have created to be part of the vPC, and there you can see the parameters that are configured and if there is a mismatch between both of them, right? So you can also look into the syslogs or the logs on the Nexus switch to see if there are any error messages seen, but you can also use this command to verify the parameters are different or not.
The type of syslog is somewhat obvious to see that if there's a mismatch, or I mean, then which area to configure?
No, so the syslogs will only point this kind of error, right?
105 on the interface port channel are being suspended. Okay, I think even that calls out, right? I mean, which is
yes,
yes,
right. But I mean, while troubleshooting, you always look at the more specific outputs. I mean, we just cannot rely on the error log, right? You need to be double sure on what you have configured. The problem is there, or probably something else. Any questions? All right. Okay, so in the later releases, in Nexus 5.02 N11 release, the config sync feature was introduced to automatically synchronize the configuration between both the Nexus switches, right? So if a particular configuration is, if a particular configuration is done on one side, it will automatically get synchronized to the other side, so that the consistency failures are less, right? The configuration transport is carried over management 0 interface using the CFS over IP. So if this config sync feature, if you're trying to use this feature, you need to ensure that in the show CFS status output, you have the CFS over IP enabled state. Okay. Any questions? I think it's very straightforward. From the lab perspective, I don't think you'll be able to use or you will get to use the config sync feature unless they ask. But it's good to know that you have an option. All right. So I'll be starting with the next topic, that is the vPC forwarding. This will help us understand how the forwarding really works with the vPC-based design, and we'll also see what are the scenarios or what will happen in case there is a failure. All right. All right, so vPC maintains a lower level topology. So the topology information is again synchronized to the vPC peers over CFS, right? Copies of the frames that are received on one vPC peer are exchanged or sent to the other vPC peer as well, so that they know what kind of frame have been received, and they can also maintain their respective MAC, they can update their MAC tables once it's received. Okay, so let's see from how the communication happens from host having MAC A and to host having MAC C. Okay, so host A sends a packet to MAC C, right? So let's name it host A, and this is host C, right? So it sends a packet to MAC C, to host C, right? So so this is the Nexus 2K, which is acting as the fabric extender. So it will just over the port channel, it will just send the packet to its primary N5K, which is the vPC peer. So the FEX runs its hash algorithm and based on selects one of the fabric uplink and sends it to the uplink Nexus device. Maybe it's 5K or 7K. The N5K1 learns the MAC address and floods it across all the ports, even over the vPC peer link as well as the other uplink vPC member ports, right? So when the N5K2 receives the flooded packet, what it does is it says that, okay, it's received from the vPC peer over the vPC peer link. and what it does is it blocks all the ports, right, from forwarding that frame across, so that if once the packet is received here, it doesn't forward it here and creates a loop. So this is in block state, and this is also in block state. So once this is received and sent across and received by the N7K2 device, right, over here, this also repeats the same process. So it floods the frame over here and floods the frame over here as well. So, right,
so only
and this
in one pair relationship, only one of them takes care of flooding, the other will be literally blocked.
Yes. Yes, it won't go, the port won't go into the block state, but it will block the forwarding of the frames on those ports.
Oh, okay.
Right?
So the role is
so instead
depending
of,
on whether it is active or
right. So there may be another host, say host B or D connected over here, and based on the hash algorithm, the FEX might have chosen to send the frame on this node. Right? So this will do the same work that was done by N5K1 over here.
Oh, okay.
Okay, makes sense? So, but if this was a STP-based design, one of those ports was already in a block state. So you didn't have an option to send packets over here.
So in such cases, that Mark 1, 2 will not happen or will happen? Will it broadcast
which
to
one?
both the ports? If that is the case, will it broadcast to both the ports? Say in switch 1, MAC A1, wherein the step 1 it receives it, and then will it go to the path 2 and alternate path also, or will it automatically go to blocks state?
No, it will not forward it across. The blocker mark is over here, right? So it will not forward it across. It will do the forwarding. It just notified it, okay, I have received, you can block the ports from forwarding this frame.
Oh, okay. So, okay.
Right? Okay. Now, the N7K2 receives the frame, floods, it does the same thing as N5K has done over here, over the vPC peerling as well as the member ports. As soon as it sends to up towards the host C, it sees that, okay, it has received, it has sent the frame successfully to MAC C, right? Now let's see what happens in the reverse path. Again, just remember the MAC address table that was built over here on the N5K1 gets over the CFS, gets replicated to N5K2 over here as well.
The same thing will be there for N7K2 and the back.
Yes. Yes.
So basically, yeah, okay.
Right. So the host C has received the packet. Now host MAC C sends the packet back to host A. N7K2 forwards the frame based on the learned MAC address. Now understand this. This was the traffic is forwarded if destination address is known, right? So it is not necessary the packet has the link on which the packet has arrived. It will forward based on the same link, right? It can send it directly to the other link. So it is independent of choosing the link. It can choose any link to forward the frame. So in this case, it has chosen the link towards the N5K2, right? And then N5K2 forwards it across the frame because it also has the MAC address of the MAC A, and it just forwards it across to the Nexus 2K over the FEX and then towards the host C. Right? So it is not necessary the packet from where the link which was used for sending the packet, the reverse path also chooses the same link. Okay. All right. Now, suppose there is any questions so far? All right. Notice over here in this scenario on both the N5Ks, right? This is the port channel 30, and this is also port channel. These are the member links of the port channel 30, right? So if you see here on N5K1, this MAC address is learned over port channel 30. Okay, and on N5K2, this is also learned over port channel 30 because this was automatically synchronized over CFS. Now, what happens when there is a failure scenario? Okay, suppose this link has got failed. So let's see now. The frame goes to switch N7K2. From there, it goes to N5K2. Now, N5K, understand there was a failure in the member link, the member port of the vPC. So it sends the frame towards the N7K1, which already knows the MAC address of the host A. And then N5K1, and N5K1 sends it over the fax to the host A. All right. So now, if you see the MAC address table for that particular host, you'll be able to see on the N5K1, it is using the same member link from which it learned the MAC address, whereas on the N5K2, it will show the link as the vPC peer link. So it is now learning the MAC address over the vPC peer link and then does the forwarding accordingly.
Say, for example, in this case, N5K and N5K2. So N5K2 would have been the secondary. So how does the CFS does the config sync in that case between the peer? So does it mean that
which one are you thinking as the secondary?
N5K2.
Right. So the synchronization was already done before, right?
So, okay.
If you go back, right, when the frame received here from host A, right, and it was flooded across both the links, right? The MAC address table is also flooded, also synchronized between the primary and the secondary vPC peer. Right? So they have both updated their MAC address table.
Okay. So that way there would be a problem in return path.
Right, exactly. Now, since the link was working fine, it had a MAC, the MAC address was pointing towards the vPC peer link. Sorry, member port, right? But when the failure was seen, the MAC address table was automatically updated to use the peer link rather than the member port because there is a failure on the member port.
Okay.
All right. Any questions?
Good.
All right. So I will stop the presentation now. 1 second.